Leaving the solar system sounds like a single act, as if there is a gate that can be passed and a sign that marks the end. In reality, the solar system has no hard outer wall. It fades through several overlapping regions, and each region can be used as a different definition of what it means to leave. The time it truly takes depends first on which boundary is chosen, and only then on how fast a spacecraft can travel. The outermost planets do not mark the end. They are only one layer inside a much larger structure shaped by the Sun's gravity and by the Sun's flowing plasma. One simple definition treats the solar system as the region containing the planets and their immediate neighbourhoods. Under that definition, leaving means passing beyond the orbit of the farthest major planet, Neptune. Neptune lies far from the Sun compared with Earth, yet it still sits deep inside the Sun's wider influence. Beyond Neptune there is no sudden emptiness. There are smaller bodies, icy objects, and long-period comets whose orbits extend far outward. A spacecraft that passes Neptune has left the planetary region in a practical sense, but it has not left the solar system in any deeper physical sense. It remains firmly within the Sun's domain. A broader definition includes the Kuiper Belt, a wide, uneven ring of icy bodies beyond Neptune. This region contains dwarf planets and countless smaller objects. It is not a dense band like a ring around a planet. It is a sparse population spread across a vast volume, with objects separated by enormous distances. If leaving the solar system means going beyond the Kuiper Belt, then the boundary is not a line but a gradual thinning of objects. A spacecraft might pass near one Kuiper Belt object and miss another by millions of kilometers, without either event carrying special meaning. Under this definition, leaving means reaching a distance where Kuiper Belt objects are rare, and where the spacecraft is moving through space that is still solar-dominated, but less populated by bound debris. Beyond the Kuiper Belt lies a region that is harder to map the outer reservoir of comets, often called the Oort Cloud. This is not a flat belt, but a roughly spherical distribution of icy bodies that can extend to distances far greater than those of the planets. It is inferred from the orbits of long-period comets that sometimes fall inward toward the Sun. The inner part of this cloud, if it exists as expected, may begin thousands of astronomical units from the Sun, and the outer part may extend tens of thousands of astronomical units. At such distances, the Sun's gravity still binds objects, but the binding is weak. Passing stars and the tidal field of the Milky Way can disturb orbits. If leaving the solar system is defined as going beyond the region where the Sun holds a cloud of comets, then leaving becomes a journey that could take thousands of years for present-day spacecraft. It also becomes difficult to specify because the cloud is not directly observed as a boundary. It is a statistical structure rather than a sharp edge. There is another way to define the solar system that does not depend on the distribution of small bodies. This definition uses the heliosphere, the bubble carved out by the solar wind. The solar wind is a flow of charged particles, mainly protons and electrons, that streams outward from the Sun in all directions. It carries the Sun's magnetic field into space and creates a vast region where the solar wind dominates over the local interstellar plasma. This region is not static. It changes with solar activity and with the pressure of the surrounding interstellar medium, yet it provides a physical boundary that can be detected by spacecraft instruments. Under this definition, leaving the solar system means leaving the heliosphere and entering interstellar space where the local plasma and magnetic field are no longer controlled by the Sun. The heliosphere itself has internal layers. Close to the Sun, the solar wind is supersonic in the sense that it moves faster than the speed of pressure waves in the plasma. As it travels outward, it expands and cools, and it eventually slows when it meets resistance from the interstellar medium. The region where the solar wind begins to slow and heat is called the termination shock. Beyond it lies the heliosheath, where the flow is slower and more turbulent. Farther still is the heliopause, the boundary, where the outward pressure of the solar wind balances the inward pressure of the interstellar medium, Crossing the heliopause is often described as leaving the solar system because it marks the end of the Sun's direct plasma dominance. Yet even after this crossing, the Sun's gravity remains, and the spacecraft is still orbiting the galaxy as part of the Sun's broader gravitational system. The heliopause is also not a perfect sphere. The Sun moves through the local interstellar medium, and this motion shapes the heliosphere. The boundary can be closer in some directions and farther out in others, like a wind-shaped bubble. Solar activity changes the pressure of the solar wind over time, shifting the boundary inward or outward. As a result, the distance to the heliopause depends on direction and on the phase of the solar cycle. Leaving the heliosphere is therefore not like passing a fixed milestone. It is like passing through a moving shoreline of plasma. A spacecraft approaching it experiences gradual changes in particle densities, magnetic field properties, and the relative influence of solar versus interstellar particles. The moment of crossing can be identified through measurements, but the region around the crossing is extended and complex. A still broader definition of leaving the solar system returns to gravity, but not in terms of the Sun's ability to hold comets. It considers the Sun's sphere of gravitational influence compared with nearby stars in the Milky Way's tidal field. The Sun's gravity dominates the motion of planets, and most small bodies out to very large distances, but beyond a certain point gravitational perturbations from passing stars in the galactic environment become comparable. This transition is gradual, not sudden. A comet far out may still be weakly bound to the Sun, yet have its orbit altered by the galaxy's tides. If leaving is defined as reaching a region where the Sun no longer acts as the primary gravitational anchor for most objects, then the boundary is diffuse and depends on time and stellar encounters. Under this definition, leaving is less a journey to a distance and more a shift into a regime where the Sun is just one gravitating object among many shaping motion. These definitions can be arranged from more immediate to more profound. Passing Neptune leaves the planetary region. Moving beyond the Kuiper Belt leaves the main known belt of icy objects. Crossing the heliopause leaves the Sun's plasma bubble and enters the local interstellar medium. Reaching the far reaches of the comet cloud if it extends as inferred leaves, the region where the Sun holds a large population of bound debris. Each of these boundaries corresponds to a different timescale for travel, because the distances differ by orders of magnitude. Without choosing the boundary, the question of how long it takes to leave cannot have a single answer. The boundary choice also reflects what is meant by truly leaving. For many purposes, leaving the realm of the planets is enough. For others, leaving means reaching a place where the environment is no longer shaped by solar wind and the Sun's magnetic field. That environment change matters because it affects radiation exposure plasma conditions and the character of interstellar particles. It marks a shift from solar weather to the background conditions of the galaxy. Yet even that shift does not remove the Sun's gravitational influence, which continues to guide the spacecraft's overall orbit around the Milky Way. The Sun remains the central mass of the solar system long after the heliopause is crossed, even though its plasma influence is left behind. The idea of leaving also carries a human intuition of isolation and remoteness. That intuition often attaches to the heliopause because it is a measurable frontier and because it represents a change in the surrounding medium. Yet the heliopause is still close in cosmic terms. A spacecraft crossing it remains far closer to the Sun than to any other star. The Sun remains the brightest and most influential nearby object. Its gravity remains the primary local force. Even the faint sunlight remains stronger than the light of other stars for a long time beyond. The craft is in interstellar space in the sense of plasma and magnetic fields, yet it is still travelling outward from the same origin, still within a region where the Sun's presence dominates the local sky. The time to leave, therefore, begins with language. Leaving the solar system can mean leaving the region of planets, leaving the region of dense, small bodies, leaving the Sun's wind bubble, or leaving the weak outer halo of bound comets. Each meaning implies a different journey length. Some meanings align with decades of travel using existing spacecraft speeds, others align with centuries or millennia. This section sets the boundary problem in its outermost form because it defines the terrain that time must cross. With the possible boundaries in view, the next step is to make distance tangible in a calm way, translating these regions into scales that can be compared without strain using the steady yardsticks of light travel time and the familiar spacing of the solar system. Distance inside the solar system is often described with numbers that feel abstract until they are tied to familiar measures. One useful measure is the astronomical unit, the average distance between Earth and the Sun. It anchors the inner system to something concrete, because Earth's orbit is the path that defines the year and the sunlight that shapes daily life. From this baseline, the other regions that matter for leaving the solar system can be placed outward in calm steps. Another useful measure is light travel time, the time it takes light to cross a distance. Light travel time does not describe how fast spacecraft move, but it gives an immediate sense of scale, because it converts distance into a simple delay. Both measures help keep the outward layers clear. Earth lies 1 astronomical unit from the Sun on average. Light travels from the Sun to Earth in a little more than 8 minutes. This means sunlight that warms Earth's surface begins its journey minutes earlier, crossing space that feels empty, but is filled with the Sun's magnetic influence and the thin flow of solar wind. The Moon is far closer. Light takes a little more than 1 second to travel from Earth to the Moon. The difference between 1 second and 8 minutes already shows how quickly scale changes even within the near neighbourhood. Mars orbits farther out than Earth, and the distance between Earth and Mars varies because both orbits are elliptical and the planets move at different speeds. When Earth and Mars are on the same side of the Sun and relatively close, light takes only a few minutes to travel between them. When they are on opposite sides of the Sun, light travel time can stretch to more than 20 minutes. These numbers are steady reminders that even the inner solar system is not a small place. They also show how the meaning of time changes with distance. A delay that is barely noticeable on Earth becomes operationally important for spacecraft. Jupiter marks the beginning of the outer planetary region in a practical sense, because it is far enough that travel times and sunlight levels change markedly. Jupiter orbits at a distance of a little more than 5 astronomical units from the Sun. Light takes tens of minutes to reach it from the Sun. From Earth to Jupiter, light travel time varies with alignment, but it is often on the order of tens of minutes. Saturn lies farther around 10 astronomical units from the Sun, with light travel time from the Sun on the order of more than an hour. Uranus and Neptune lie farther still at distances of roughly 20 and 30 astronomical units. Sunlight at those distances is much weaker than at Earth, and the travel time for light from the Sun reaches several hours. These timescales remain small compared with the years required for spacecraft travel, but they locate the outer planets as still within a region where sunlight, though faint, remains a practical presence. Beyond Neptune, the solar system continues without a clean break. The Kuiper Belt occupies a broad zone beyond the orbit of Neptune, extending outward for tens of astronomical units. It is helpful to picture it not as a ring, but as a thick, sparse region, a population of icy bodies spread across a wide range of distances and inclinations. A spacecraft moving outward from the Sun does not cross a single line and declare the belt reached. It gradually enters a region where such bodies are more likely to be found, though still separated by enormous empty volumes. Light travel time from the Sun to this region is measured in several hours, and from Earth the delay adds another few minutes beyond that, depending on geometry. Farther out the distance becomes so large that astronomical units begin to lose intuitive power. Yet they remain useful because they show the orders of magnitude involved. 1,000 astronomical units is 1,000 times Earth's average distance from the Sun. Light would take several days to travel that far from the Sun. A 10,000 astronomical unit distance corresponds to light travel time on the order of weeks. These distances are still not interstellar in the sense of reaching another star because the nearest star is more than 200,000 astronomical units away. That comparison matters because it shows that a very extended solar system, if defined by distant comets, begins to overlap in scale with the separation between stars yet remains substantially smaller than the distance to even the nearest stellar neighbour. Light travel time provides another calming perspective because it sets a universal yardstick. A distance of one light day is the distance light covers in one day. A light week is the distance light covers in 1 week. These are still small compared with a light year, yet they are enormous compared with the orbits of planets. If a boundary is a light day from the Sun, it is far beyond the planets and far beyond the Kuiper Belt. If a boundary is a light week from the Sun, it is far into the realm where the solar wind has long since changed character, and where the density of bound small bodies, if they exist, there is extremely low. When distances are expressed this way, the question of leaving becomes a question of whether the chosen boundary lies hours, days, or weeks of light travel time away. The heliosphere adds another distance scale that is distinct from the distribution of solid objects. The solar wind expands outward and interacts with the surrounding interstellar medium. The boundary where solar influence in plasma terms yields to interstellar conditions lies at distances that can be described in astronomical units and also in light hours. The light travel time from the Sun to such a boundary is still only on the order of many hours, not days or weeks. This reveals an important fact. The heliosphere, though vast by human standards, remains small compared with the distances between stars. Crossing the heliopause places a spacecraft in interstellar plasma, yet it remains in a region of space where sunlight is still far stronger than starlight from other suns, and where the Sun's gravity remains the dominant local gravitational pull. The same outward distances can also be compared to the pace of typical spacecraft. Many interplanetary missions travel at speeds measured in tens of kilometers per second during cruise, though their speeds change with gravitational assists and with their specific trajectories. At such speeds, a spacecraft travels a fraction of an astronomical unit per day. Over a year it can travel many astronomical units, but not hundreds or thousands. This contrast between light travel time and spacecraft travel time is central. Light crosses the solar system in hours. Spacecraft cross it in years. This difference is why leaving the heliosphere, a boundary only hours of light travel time away, can still take decades for a probe. It is also why leaving the far comet reservoir, if that is the chosen boundary, can take millennia. Another way to make distance tangible is to consider the spacing between orbital paths as a kind of outward ladder. Earth's orbit is a tight circle on this ladder. The outer planets sit many rungs outward. Yet even Neptune's orbit is still on the inner side of the Sun's larger physical domains. The Sun's gravitational influence extends far beyond Neptune, and the Sun's plasma influence extends beyond the planetary region as well. The ladder does not end at Neptune. It continues into regions where the rungs are not planets, but statistical populations and physical transitions. In this context, the phrase truly take to leave can be understood as a comparison between human expectation and physical scale. Human intuition is shaped by travel on Earth, where crossing a continent can take hours by aircraft, and where the horizon feels close. In the solar system, even the nearest outer boundaries are so distant that travel times become measured in years, and some boundaries are so distant that travel times become measured in generations. The distance is not only a number, it is a demand placed on power systems, navigation, stability, communications, and the slow wear of time on hardware. Distance also matters because it influences the environment. Sunlight weakens outward, making solar power less effective and thermal control different. the solar wind changes character, and the influence of interstellar particles grows. The density of dust and small bodies changes. These shifts do not happen at a single line, but they correlate with distance. Describing distance in light time and in astronomical units helps keep these environmental changes connected to a physical scale rather than to a vague sense of far away. With the main boundaries now placed on a calm distance map, the question becomes one of speed, because speed converts these distances into real mission durations. A spacecraft does not travel at light speed. It travels at speeds set by propulsion and by gravity assists. To understand how long leaving truly takes the next inward step is to examine the speeds that spacecraft can realistically sustain, and why those speeds, though impressive, remain small compared with the size of the solar system. Time to leave the solar system is set primarily by speed, because the distances involved are fixed by astronomy, while spacecraft velocities are limited by propulsion and by the energy that can be carried. Spacecraft speeds can sound fast in everyday terms. Tens of kilometers per second is far faster than any aircraft. Yet on solar system scales, even such speeds are slow. A journey measured in tens of astronomical units becomes measured in years. A journey measured in hundreds of astronomical units becomes measured in decades. When the boundary is thousands of astronomical units away, the same speed implies centuries. The true feeling of duration emerges from this mismatch between human-scale speed and solar system-scale distance. Spacecraft do not simply accelerate once and then maintain a chosen cruising speed. Their speeds are shaped by gravitational fields and by mission design. Most missions begin by sharing Earth's orbital speed around the Sun, then add energy through launch and burns. In the Sun's frame, a spacecraft leaving Earth begins already moving quickly, because Earth itself moves around the Sun. Leaving the solar system is therefore not a matter of starting from rest. It is a matter of changing the shape and energy of an orbit around the Sun until it becomes a trajectory that carries the craft far outward. Typical deep space missions achieve heliocentric speeds measured in tens of kilometers per second. This number can rise higher during close passes by planets or by the Sun, but what matters for leaving is the long-term outbound speed at great distance, when the Sun's gravity has weakened and the craft has settled into a nearly constant cruise. The Sun's gravity continually slows an outward-moving spacecraft, converting kinetic energy into gravitational potential energy as the craft climbs outward. If the spacecraft is not given enough energy to escape, it will eventually slow to a stop and fall back. If it is given more than enough energy, it will still slow as it climbs, but it will retain a residual speed far from the Sun. This residual speed is what determines how quickly it crosses the outer boundaries. The energy given to a spacecraft is often described in terms of escape from the Sun, not just escape from Earth. Escaping Earth places the craft in an orbit around the Sun similar to Earth's, but with a slightly different shape. Escaping the Sun requires adding enough energy that the craft's heliocentric trajectory becomes unbound. Most missions within the solar system remain bound to the Sun, moving on elliptical orbits that return inward unless they are designed for escape. Missions that leave the solar system must reach a heliocentric escape trajectory, often with the aid of planetary gravity assist that add energy, without requiring additional fuel. Even with escape energy, outward speed is not constant near the Sun. The craft moves fastest when it's close to the Sun and slows as it moves outward. Over time, the speed approaches a steady value relative to the Sun as the gravitational pull becomes weaker. That steady value may be only a small fraction of the speed near the Sun. For leaving the heliosphere, the cruise speed in the outer solar system is the key number, because most of the travel time is spent far from the Sun, covering long distances at that steady pace. This is why a mission can reach Jupiter relatively quickly, yet still take decades to reach the heliopause. The inner distance is crossed during a period of higher speed and stronger gravitational shaping, while the outer distance is crossed during long coasting. Spacecraft speed is limited by the change in velocity that propulsion can provide. Chemical propulsion provides high thrust, but limited total change in velocity for a given mass ratio. Once a spacecraft has left Earth, it can use upper stages and onboard engines to adjust its path, but for large outbound speeds, carrying enough propellant becomes difficult. Gravity assists can add significant energy, but they require specific planetary alignments and close flybys, and they often involve long travel times to reach the assisting planet in the first place. A mission might wait years for a favourable alignment that allows a sequence of assists. The time spent waiting, though not part of the travel after launch, is part of the true timeline of achieving a fast departure. The fastest departures from the inner solar system often involve passing close to a massive planet like Jupiter to gain energy. Jupiter's gravity can bend a trajectory and transfer some of Jupiter's orbital momentum to the spacecraft, increasing heliocentric speed. This does not violate conservation laws because Jupiter loses an imperceptibly small amount of momentum in the process. The spacecraft gains speed relative to the Sun, and this gain can shorten the time to reach distant boundaries. Yet the gain is bounded. Jupiter can provide only so much energy without the spacecraft coming dangerously close, and the geometry of the encounter matters. The craft's path must be arranged precisely. After the encounter, the craft still coasts outward, slowing gradually as it climbs away from the Sun. The final outward speed far from the Sun is still in the range of tens of kilometers per second for realistic missions. There's also the option of using the Sun itself for a gravity and energy strategy. A spacecraft can fall inward toward the Sun, reaching high speed near perihelion, then use propulsion at that point to gain more energy than the same burn would provide far away. This is known as the Oberth effect. Because a burn at high speed changes orbital energy more efficiently, it can be used to increase outbound speed. This strategy has been proposed for rapid outer solar system and interstellar precursor missions, but it requires a spacecraft that can survive close to the Sun's intense heat and radiation, and it still requires substantial propulsion capability. It can raise outbound speed, but not without engineering cost and mission risk. As the spacecraft travels outward, the environment changes in ways that affect speed indirectly. Solar power becomes less effective limiting electric propulsion unless large arrays are carried. Deep space navigation remains possible, but communications weaken with distance, reducing the ability to adjust plans quickly. If the spacecraft relies on continuous thrust such as electric propulsion, the ability to generate power and manage waste heat becomes part of the speed story. If the spacecraft is purely coasting, then speed is mostly fixed after its last major propulsion event. For most probes that leave the solar system, the outbound speed after planetary assists is essentially the speed that carries them to the heliopause and beyond. With a steady outward speed, travel time becomes distance divided by speed, but with the added reality that speed is not perfectly steady. The craft is slowed by the Sun's gravity, and it may also be nudged slightly by pressure from sunlight or by small propulsion adjustments. For large distances, these details matter less than the broad average. The broad average is that current deep space probes move outward at speeds that carry them a few astronomical units per year. At that rate, crossing tens of astronomical units takes decades. Crossing hundreds takes centuries. This is the central reality behind the question. Leaving the solar system is not slow because of a particular obstacle. It is slow because practical spacecraft speeds are small compared with the distances to the most meaningful boundaries. This speed limitation also explains why there is a difference between leaving the planetary region and leaving the heliosphere. The planetary region extends to a few tens of astronomical units. The heliosphere extends to more than 100 astronomical units in many directions. The outer comet reservoir, if used as the boundary, extends thousands to tens of thousands of astronomical units. Each boundary is an order of magnitude farther than the previous, and spacecraft speed does not increase by an order of magnitude to match. As a result, the time to leave grows by orders of magnitude as the chosen boundary moves outward. The speed story begins on Earth, because the maximum outward speed a spacecraft can achieve is strongly shaped by how it leaves Earth and how much energy can be added early in the mission. The next inward step is therefore to examine Earth departure itself, not as a dramatic launch, but as a disciplined sequence of velocity changes that determine the starting conditions for everything that follows. The journey to leave the solar system begins long before a spacecraft reaches the outer planets. It begins at Earth's surface, where a vehicle must overcome gravity and atmosphere to reach a state where it can move freely. The change in velocity required to reach orbit is large, and the change in velocity required to depart Earth entirely is larger. These early velocity changes are costly, because propellant must be lifted along with the payload. The shape of the departure, the chosen parking orbit, and the timing of the escape burn all influence the spacecraft's final speed relative to the Sun. The true time to leave therefore includes the reality that the first steps are constrained by Earth's gravity well, and by the rocket architectures that can operate within it. To reach low Earth orbit, a rocket must provide enough change in velocity to build a high horizontal speed while climbing out of the dense atmosphere. Atmospheric drag and gravity losses add to the requirement. The rocket must also carry structural mass engines, guidance systems, and the payload itself. This is why most of a launch vehicle's mass is propellant. The initial propellant mass is not used to create outward solar system speed directly. It is used to create the basic condition of being in orbit where a spacecraft can coast without continuous thrust, and where it can plan precise burns without falling back to Earth. Once in orbit, a spacecraft can depart Earth by performing a burn that raises the farthest point of its orbit until the orbit becomes unbound. This is Earth escape. The resulting path is often a hyperbola relative to Earth, meaning the spacecraft will not return. Earth escape speed at the point of departure depends on how much energy the spacecraft has in its parking orbit and how much additional energy its engines or upper stage can provide. A spacecraft that escapes Earth does not necessarily escape the Sun. It joins the wider solar system on a heliocentric trajectory that still lies within the Sun's gravitational field. The heliocentric path after Earth escape depends on the direction of the departure relative to Earth's orbital motion. Earth's orbital speed around the Sun is a significant contribution. By departing Earth in the direction of Earth's motion, a spacecraft can add to its heliocentric speed. By departing opposite Earth's motion, it can subtract. This is why missions to inner planets often launch in a way that reduces heliocentric energy, while missions to outer planets often launch in a way that increases it. The spacecraft's heliocentric trajectory is therefore built on top of Earth's own orbital motion. A mission that aims to leave the solar system seeks to maximize outward heliocentric energy within the constraints of launch vehicle performance and mission safety. A common mission profile uses a high-energy upper stage that performs the Earth escape burn soon after reaching parking orbit. For deep space missions, the launch vehicle may inject the spacecraft directly onto an Earth escape trajectory without a long coast in orbit. Alternatively, the spacecraft may coast in Earth orbit for some time and then fire its own engines at a precise moment. The timing is chosen so that the departure direction sets the spacecraft on the desired heliocentric path. Small differences in timing and burn accuracy can lead to large differences over years of travel. This is why deep space navigation and tracking begin early, even while the spacecraft is still close to Earth. The energy available from launch vehicles is often described by how much mass they can send to escape at a given departure speed. If a mission requires a high departure speed, the allowable payload mass decreases. This is another expression of the mass penalty already present in rocketry. Sending a heavy spacecraft to a high-energy trajectory is difficult. Many missions trade mass for speed, carrying less propellant and fewer instruments, in order to depart faster, or accepting a slower departure in order to carry more capability. For leaving the solar system, higher speed shortens the travel time to outer boundaries, yet it also reduces payload margin, which can reduce power communications and redundancy. A faster mission may therefore be more fragile. A slower mission may be more robust but takes longer. The true timeline is tied to this design trade. After Earth escape, the spacecraft enters a heliocentric orbit that depends on the energy of departure. If the heliocentric trajectory is still bound, it will be an ellipse that may take the spacecraft outward to a far distance, and then back inward unless additional energy is added. Many missions to outer planets use such bound transfer ellipses, and then rely on planetary gravity assists to reshape the trajectory into an escape path. If the heliocentric trajectory is unbound from the start, the spacecraft is already on a solar escape trajectory. Even then, the Sun's gravity slows it as it moves outward, leaving a finite residual speed at great distance. This residual speed is what determines how quickly the spacecraft reaches the heliosphere boundary and beyond. For missions that aim to maximize residual speed, planetary gravity assists are often essential. Earth departure alone rarely provides enough energy to produce the highest possible outward speed for a given payload. A spacecraft may be launched onto a path that reaches Jupiter, where it can gain additional energy. This means the Earth departure phase is designed not only to escape Earth, but to arrive at Jupiter with the right approach, angle, and timing. The mission's early trajectory is therefore shaped by a chain of constraints. It must leave Earth at the right time of year to align with Jupiter's position. It must perform correction burns to refine the approach. It may need to pass through the inner solar system in a way that sets up a later sequence. The practical result is that the fastest outward paths are not always the most direct. They can involve complex geometry that is chosen to gain energy, rather than to minimize distance. Earth departure also introduces the first major environmental transitions. The spacecraft moves from atmosphere to vacuum, from strong gravity to microgravity, from constant ground control contact to the beginnings of communication delay. These transitions matter because they set the early reliability demands. Many spacecraft failures occur early during deployment and initial operations. A mission intended to leave the solar system must survive this early period, then operate reliably for decades. The departure phase therefore includes careful commissioning, calibration of instruments, and validation of power and thermal systems. These steps take time and may influence when the spacecraft begins its long outward cruise. The clock for leaving can be measured from launch, but the functional timeline of the mission includes the early period when the spacecraft becomes a stable, autonomous traveler. For human missions, Earth departure imposes additional constraints because crew safety must be assured during launch and any abort scenarios must be addressed. Yet even for uncrewed probes, the departure phase sets the energy ceiling. In practice, the maximum outward speed achievable by a spacecraft is strongly limited by the change in velocity that can be delivered by the launch system and by any early propulsion stages. This is why leaving the solar system is for now primarily a question of how much energy can be added in the first hours and days, and how effectively gravity assists can amplify that energy later. Having established Earth departure as the foundation of outward speed, the next inward step is to follow the outbound path through the inner solar system, where the Sun's gravity shapes motion, and where early travel times can feel fast compared with the long cruise that follows. This reveals why the first few years of an outward mission can include dramatic milestones, while the true act of leaving takes much longer, dominated by steady coasting through the outer darkness. After Earth departure, an outward-bound spacecraft enters a phase that looks like open travel, but is still tightly governed by gravity. In the inner solar system, the Sun's pull remains strong, and trajectories curve as the spacecraft follows an orbit around the Sun. Even when the mission is destined to leave the solar system, its early path is often an arc shaped by orbital mechanics, rather than a straight outward line. During this phase, distances in astronomical units can be crossed within months, and the spacecraft can pass familiar landmarks, such as the orbits of Mars and the asteroid belt region. These early milestones can create an impression of rapid progress, yet they occur while the spacecraft is still relatively close to the Sun, still moving at higher speeds, and still within a region where the remaining distance to meaningful outer boundaries is much larger than what has been covered. The true timeline begins to reveal itself here in the contrast between early motion and later coasting. The spacecraft's heliocentric trajectory after Earth escape is determined by its energy and direction. If it is headed outward to the outer planets, it typically moves onto an orbit with a larger semi-major axis than Earth's, and therefore a longer orbital period. For many missions, the spacecraft is still bound to the Sun, at this stage travelling on an elliptical path that will intersect the orbit of a target planet such as Jupiter or Saturn. The spacecraft speeds up as it falls inward toward the Sun, and slows as it climbs outward even during the same orbit. Because the departure begins near Earth, the craft often starts with a relatively high heliocentric speed, then gradually slows as it moves outward. This slowing is not due to friction. It is the exchange between kinetic energy and gravitational potential energy in the Sun's field. In the first months, the spacecraft crosses the orbits of near-Earth space and Mars. The distances here are large compared with Earth travel, but small compared with the outer solar system. Communication delays grow from seconds to minutes. Sunlight remains strong enough for solar power if the spacecraft is designed to use it. Thermal conditions are still dominated by the Sun's heating. Navigation relies on frequent tracking and small trajectory correction maneuvers that refine the path. These maneuvers are usually small compared with the main departure burn, but they are essential because arriving at a planet for a gravity assist or a flyby requires passing through a narrow target region millions of kilometers away. The spacecraft then moves toward the asteroid belt region, which is often misunderstood as a dense field. In reality, the main belt is a vast volume, with large separations between objects. Most spacecraft pass through it without close encounters. The practical significance of this region is not collision risk, but the shift in distance scale. The belt lies a few astronomical units from the Sun. A spacecraft can reach it within months to a year, depending on its trajectory. This seems far until it is compared with the tens and hundreds of astronomical units required to reach the heliosphere boundary. Passing through the belt is a small fraction of the full journey to leaving the Sun's plasma bubble. As the spacecraft continues outward, it approaches the orbit of Jupiter. For many missions, Jupiter is the key turning point because it is massive and can provide a gravity assist that adds energy to the outward trajectory. Reaching Jupiter typically takes years, not months, because the spacecraft must match the geometry of Jupiter's orbit, and because low-energy transfer paths are often chosen to fit launch vehicle capability and mission safety. During this time, the spacecraft remains in a region where solar power is still possible, though weaker than at Earth. The communication delay grows to tens of minutes. The spacecraft's operations become more autonomous because real-time control is impossible. A Jupiter encounter, if used, is a moment when the spacecraft's path can change quickly, but the encounter does not make the craft instantly far away. It changes the craft's speed relative to the Sun and its direction. After the encounter, the spacecraft continues outward again, slowing gradually as it climbs away from the Sun. The major difference is that it now carries a higher residual speed, which will matter most in the outer decades of travel. The encounter can shorten the time to the heliopause by increasing the number of astronomical units the craft covers per year. Yet even a significant increase still leaves the craft travelling in a regime where tens of years are required to reach the boundary. After Jupiter, some missions pass Saturn, Uranus, or Neptune depending on their goals and gravity assist sequence. Each additional planetary encounter can reshape the trajectory, but each encounter also imposes a timing constraint because planets must be in the right positions. A mission that aims for maximum outbound speed might accept a path that is longer in distance but better in momentum gain. This is one reason why the outward track on a map can look indirect. It is not wandering. It is a path that trades distance for energy in a way that reduces total time to the farthest boundaries. As the craft moves beyond the outer planets, the character of travel changes. The sun's pull weakens and the craft's speed becomes closer to its long-term cruise value. At the same time, the environment becomes colder in terms of reduced solar heating, and sunlight becomes too weak for most practical solar power systems unless they're extremely large. Many deep space probes rely on radioisotope power systems in this region, producing steady but limited electricity. Limited power shapes the mission. Instruments must be scheduled. Transmitters must conserve energy. The spacecraft becomes a quiet, slow-moving node in the dark operating with long intervals between active periods. This is the point where leaving the solar system becomes a long-duration process rather than a sequence of milestones. The outer distance from the orbit of Neptune to the heliopause is several times the distance from the Sun to Neptune itself. Even if the spacecraft has already travelled for a decade to reach Neptune, it may still have another decade or two before it reaches the heliopause depending on its outward speed and on the actual distance to the boundary in its direction of travel. This is why the phrase truly take matters. The planetary region is a minority of the full distance to the heliosphere boundary. A spacecraft can visit outer planets within a human career span, but it takes longer to reach the point where solar wind dominance ends. The early cruise also involves gradual changes in navigation and tracking. As the craft moves farther, tracking accuracy decreases because signals are weaker and delays are longer. Yet navigation remains possible through careful measurement of radio signals, and in some missions through optical navigation using star fields and known objects. Course correction maneuvers become less frequent because propellant is limited, and because the spacecraft's trajectory is now largely set. Small errors accumulate slowly, but over years, even small errors can matter for passing near a target or for pointing antennas accurately. The mission's ability to maintain precise attitude control becomes part of the long timeline of leaving, because losing pointing can end communications even if the spacecraft remains functional. In this outward phase, time is also shaped by the need to manage the spacecraft's internal health. Systems must be kept within temperature limits. Components must be powered on and off to preserve life. Memory must be managed. Software must remain reliable over decades. These needs create an operational rhythm that is slow and deliberate. The spacecraft is not racing, it is enduring. With the early outbound phase traced from Earth, past the inner system, and toward the long cruise, the next inward step is to look directly at the asteroid belt region in clearer detail. This is not because it is a major obstacle, but because it is a common point of misunderstanding. Clarifying what it is and what it is not helps keep the scale of leaving the solar system honest, preventing a dramatic image from replacing the quiet reality of vast, mostly empty space and steady motion over many years. The asteroid belt region sits between the orbits of Mars and Jupiter, and it often appears in imagination as a crowded field of tumbling rocks. In reality, it is a wide, sparse population of bodies separated by immense distances. A spacecraft crossing it usually experiences nothing visible at close range. The belt matters for the question of leaving the solar system, not because it is a barrier, but because it is an early outward landmark that can make deep space seem closer than it is. Many people picture the belt as a dramatic threshold. For travel times, it is simply one more part of the inner journey reached relatively quickly, compared with the long cruise that follows. Understanding the belt clearly helps anchor what is truly slow about leaving not hazards early on but distance and speed in the outer darkness. The main asteroid belt occupies a region a few astronomical units from the Sun. Its exact extent is not defined by a wall but by a distribution with many objects concentrated in certain orbital ranges and fewer in others. The belt contains bodies ranging from tiny fragments to large asteroids and dwarf planet-sized objects. The total mass of the belt is small compared with a planet. It is distributed across a volume so large that the average separation between substantial asteroids is vast. A spacecraft travelling through the belt does not need to weave between rocks. It travels through mostly empty space. The probability of collision is low, and spacecraft do not treat the belt as a navigational obstacle in the way a dense debris field would be treated. The belt's presence is often inferred through observation and through the gravitational signatures of its larger members. Spacecraft have visited several asteroids and have travelled through the belt many times. These missions confirm the sparsity. When a spacecraft does encounter an asteroid, it is because the mission has been deliberately targeted to do so, adjusting its trajectory to meet a small object in a large region. This targeting requires precise navigation and sometimes additional propulsion, which itself influences mission timelines. In other words, visiting asteroids takes time not because the belt blocks passage, but because the objects are far apart and require intentional rendezvous. For an outbound spacecraft that is not stopping the belt is crossed as part of a heliocentric trajectory that continues outward. The travel time through the belt depends on the spacecraft's speed and the path's geometry, but on the scale of leaving the solar system it is relatively brief. A spacecraft may pass from the orbit of Mars into the belt region within months, and it may traverse the belt region on the way to Jupiter over the course of a year or two depending on its transfer orbit. These are long times by Earth standards, but they are short compared with the decades required to reach the heliosphere boundary. The belt also provides a useful contrast between object-based boundaries and physical boundaries. If leaving the solar system were defined by leaving regions of solid bodies, one might be tempted to see the belt as a kind of edge. Yet beyond the belt lie the giant planets and their moons, which contain far more mass and more complex environments than the belt. Even beyond the planets there are the Kuiper Belt and other populations of small bodies. The belt is not the end of anything. It is a concentration of material within the broader sun-centered structure. Its significance is historical and scientific, not definitional for leaving. The belt does influence travel indirectly through gravity. Jupiter's gravity dominates the belt's dynamical structure, creating gaps and resonances where asteroid orbits are perturbed. For spacecraft, this gravitational structure is not a hazard, but it shapes the broader architecture of the solar system. It reflects how the mass of Jupiter affects trajectories and how missions to the outer solar system often aim for Jupiter encounters to gain energy. The belt therefore sits as a region on the path to the most powerful gravity assist. It is a waypoint on the way to a more important momentum exchange. The belt also marks a region where sunlight remains strong enough for solar power systems to work comfortably. At a few astronomical units, sunlight is weaker than at Earth, but still sufficient for many spacecraft, especially if they carry arrays sized appropriately. Thermal control remains manageable through radiators and insulation. Communications delays remain measured in minutes. These conditions are still part of the inner solar system environment, where operations can be closely managed from Earth despite delays. This operational comfort contrasts with the far outer regions where sunlight becomes too weak for most solar power designs, where radioisotope or nuclear systems become more important, and where communications delays and weak signals limit data rates. The belt, therefore, represents a stage in the outward journey where travel is still within a relatively familiar regime. For human travel, the belt is also not a fundamental obstacle. The primary constraints for humans remain life support, radiation, microgravity, and mission duration. A crewed ship could pass through the belt without special measures beyond those already needed for deep space travel. The belt's low density does not add significant additional impact risk, compared with the background micrometeoroid environment. The psychological image of a hazardous belt is not aligned with the physical reality. The hazard of human travel begins to grow not at the belt, but with time spent outside Earth's protective magnetic field, and with the long durations required to reach farther targets. The belt can, however, be part of a realistic outward infrastructure strategy. Some asteroids contain water-bearing minerals and metals that could in principle be used for propellant production and construction. If a spacefaring civilization were to develop large-scale resource extraction, the belt and near-Earth asteroids could become sources of material that reduce dependence on launching everything from Earth. This could eventually make deep space missions more feasible by lowering the mass that must be lifted from Earth's gravity well. Yet building such industrial capability is a long-term project that itself requires extensive infrastructure power and transportation. It does not shorten the immediate travel time for a single probe leaving the solar system. It is a pathway for changing the economics and scale of space operations over decades. The belt then is best understood as a region that is crossed early in the outward journey, and as a reminder that even the most famous far places in the solar system are close compared with the boundaries that truly mark departure from the Sun's immediate environment. Passing the belt does not mean a spacecraft is near the edge. It means it has begun to move beyond the inner worlds. The real stretch of leaving begins after the outer planets, where the spacecraft's speed settles into a long cruise, and where the remaining distance to the Heliosphere boundary is still vast. The next inward step is to move from this clarified inner landmark to the outer planets themselves, because those encounters are the last major gravitational tools available within the solar system. They also anchor the public sense of distance, since reaching them already takes years. By tracing the timeline to the outer planets and beyond, the long scale of the final cruise becomes clear, and the difference between visiting Neptune and truly leaving the Sun's bubble can be held without strain. The outer planets represent the last large milestones on the way out. They also represent the last major sources of gravitational leverage because their mass can bend and energize trajectories. Reaching them already takes years even for fast missions, and that fact helps ground what leaving truly means. If it takes many years to reach the orbit of Neptune, then leaving a boundary several times farther away cannot be expected to take only a little longer. The outer planets are not close to the edge. They are midpoints on a much longer outward path to the Heliosphere boundary, and they are tiny steps compared with any boundary defined by distant comet populations. Jupiter is the nearest of the giant planets, and is often reached within a few years of launch. The exact time depends on trajectory, choice, launch energy, and mission design. Low-energy transfers can take longer but allow heavier payloads. Higher-energy transfers can arrive sooner but demand more departure energy and often reduce payload mass. Jupiter is important because it can supply a significant gravity assist. A spacecraft can pass behind or ahead of Jupiter relative to its motion and emerge with a different heliocentric speed and direction. This can be used to send a craft inward toward the Sun, outward towards Saturn, and beyond or out of the plane of the planets. For leaving the solar system, Jupiter's role is often to increase outbound heliocentric energy, so that the craft's residual speed far from the Sun is higher. Saturn lies farther out, and is often reached several years after Jupiter if the mission includes both. Saturn can also provide gravity assists, though its mass is smaller than Jupiter's and its orbital speed is lower. In some mission designs, Saturn's role is to shape the path toward Uranus or Neptune, or to send a craft out of the ecliptic plane. A sequence of assists can add energy step by step, but each assist requires time to reach the planet and requires the planets to be in favorable positions. These timing constraints can dominate mission design. A path that yields the highest outbound speed might require launching in a specific year and following a multi-planet route that cannot be repeated easily for decades. This means the fastest possible escape trajectories are not always available on demand. They are tied to celestial schedules. Uranus and Neptune are much farther. A spacecraft travelling outward to these planets typically requires a decade-scale cruise. The path can be direct, but often it is assisted by Jupiter and sometimes by Saturn. These trajectories are chosen to balance payload mass, travel time, and mission risk. Reaching Uranus and Neptune demonstrates the slow truth of solar system travel. Even with gravity assist and high-energy departures, a spacecraft remains moving at a speed that makes tens of astronomical units a multi-year journey. Neptune's distance, around 30 astronomical units from the Sun, is a useful reference. The heliosphere boundary that defines leaving in plasma terms lies several times farther away in many directions. A mission that reaches Neptune has not completed even half the outward distance to that boundary. After passing Neptune's orbit, the spacecraft enters the region associated with the Kuiper Belt. This is where sunlight is very weak compared with Earth, and where solar-powered propulsion and systems become less practical, unless built at large scale. Most spacecraft in this region rely on internal power sources if they are expected to operate for long times. Communications become challenging because signal strength falls with the square of distance, and the spacecraft must use limited power to transmit. Data rates drop, and mission teams must plan for sparse communication windows and long integration times to receive faint signals. In this sense, the environment of leaving begins to feel different well before any formal boundary is crossed. The spacecraft becomes more isolated operationally as distance grows. The long cruise beyond Neptune is dominated by steady motion. The spacecraft's residual speed relative to the Sun is nearly constant, and its progress can be thought of as a number of astronomical units per year. Even small differences in this speed matter over decades. A craft that gains an extra few kilometers per second at Jupiter can reach the heliopause several years earlier. Yet the gains are limited. They do not compress decades into a few years. The distance from Neptune to the heliopause is measured in many tens of astronomical units. At typical outbound speeds, that distance corresponds to decades. This is why the true time to leave is often surprising. The most visible planetary milestones occur in the first decade or two, while the final crossing of the heliosphere boundary can occur only after decades of quiet travel. The outer planets also demonstrate another aspect of the timeline: the need for durability. A spacecraft going to Neptune must operate reliably for a decade before it even reaches its target. If it then continues outward to the heliopause, it must operate reliably for another decade or more often, with declining power and aging components. The time to leave is therefore not only a geometric division of distance by speed, it is constrained by whether the spacecraft can remain functional long enough to reach the boundary and measure its crossing. A spacecraft can physically pass through the heliopause, even if it is dead, but the mission's ability to confirm leaving depends on operating instruments and communications at that time. The true leaving as a human-known event requires that the craft still speaks. Beyond Neptune, the Sun's gravity still shapes motion, but the craft is now so far away that planetary perturbations become small. The path is almost a straight line when viewed on small scales, though it remains a curve in the Sun's gravitational field on larger scales. The craft's attitude control remains critical. To communicate, it must point antennas accurately at Earth. Maintaining pointing over decades requires fuel for small thruster firings, or reaction wheel systems with desaturation maneuvers. Fuel is limited. Reaction wheels can fail. Sensors drift. The long timeline to leave is therefore tied to careful management of these small resources. Many years of outward travel can be ended by a small component failure. This is part of why building fast missions with low mass can be risky. Less mass often means fewer redundancies and smaller margins. The outer planets also mark a shift in cosmic background. Interstellar particles begin to appear in measurements even before the heliopause is crossed, and the solar wind becomes more structured and variable. The spacecraft travels through a region where the sun's influence is weakening in plasma terms, yet the transition is gradual. There is no single change that happens at Neptune. The true boundary lies farther out, and the spacecraft must continue through years of slowly changing conditions. For definitions of leaving that rely on the Oort Cloud, the outer planets are only the beginning. The distances to the inferred comet reservoir are orders of magnitude larger than the distance to Neptune. At present, spacecraft speeds reaching such distances would take thousands of years. The outer planets therefore provide a reality check. If the farthest planet takes a decade-scale journey, then leaving a boundary tens or hundreds of times farther cannot fit within a human lifetime unless speed increases dramatically. With the outer planets placed in the timeline, the next inward step is to examine gravity assists explicitly, because they are the main reason some spacecraft leave faster than others. Gravity assists can raise outbound speed, but they also bind missions to specific geometries and long preparation cycles. Understanding their trade makes it clearer why leaving is slow even for the fastest plausible trajectories within current physics. Gravity assists are the most effective tool currently used to shorten the time it takes to reach the far outskirts of the Sun's domain. They do not create thrust. They rearrange energy and momentum by using a planet's gravitational field as a moving slope. When a spacecraft passes near a planet, it falls toward the planet and then climbs away, leaving with roughly the same speed relative to the planet as it arrived, aside from small effects and any engine burns. The key is that the planet itself is moving around the Sun. In the Sun's frame, the spacecraft can leave with a different speed than it had before the encounter. It can steal a small amount of the planet's orbital momentum, increasing its own heliocentric speed. The planet's change is too small to measure in practice, but the spacecraft's change can be large. This is why gravity assists have enabled missions to the outer solar system and beyond, with propulsion systems that would otherwise be insufficient. The benefit of a gravity assist depends on geometry. The spacecraft's path relative to the planet determines whether it gains heliocentric speed, loses it, or changes direction. Passing behind a planet relative to the planet's direction of motion tends to increase heliocentric speed. Passing ahead tends to decrease it. The closest approach, distance, also matters. A closer pass allows a sharper turn and a larger change in heliocentric velocity, but it also increases risk from planetary radiation, belts ring particles, or atmospheric drag if the pass is too low. The spacecraft must thread a safe corridor that still provides meaningful energy gain. For leaving the solar system, the most valuable assists are typically from Jupiter and sometimes from Saturn. Jupiter is massive and moves quickly around the Sun, making it a strong source of momentum exchange. A well-designed Jupiter flyby can significantly increase a spacecraft's outbound speed. Yet the spacecraft must first reach Jupiter, which takes time. It must also arrive on a trajectory that sets up the desired outbound direction. If the goal is to head out of the ecliptic plane or toward a particular region of the sky, the assist must be planned accordingly. The assist is therefore not a universal shortcut. It is a tailored maneuver that commits the spacecraft to a specific path. Gravity assists also create schedule constraints that are larger than the mission itself. Planets move, and alignments that allow a particular sequence occur only at certain times. Some famous multi-planet opportunities occur rarely. If a mission requires Jupiter, Saturn, and another planet in a sequence that yields maximum outbound speed in a particular direction, the launch window might occur only once in a generation. Missing the window can mean waiting many years. This waiting is part of the true time to leave in a practical sense, because it determines when a fast trajectory is even available. A slower trajectory might be available more often, but it would lead to a longer cruise time to the heliosphere boundary. There is also a trade between outbound speed and mission complexity. Each planetary encounter requires precise navigation, and a robust spacecraft that can survive the environment near the planet. Jupiter's radiation belts are intense. A close pass can expose electronics to high radiation doses. Saturn's rings contain particles that must be avoided. Each encounter requires careful trajectory correction maneuvers over years to ensure the spacecraft arrives at the right point in space at the right time. These correction maneuvers consume propellant and depend on functioning attitude control and communications. A mission with multiple assists is therefore more fragile in some ways than a mission with a single direct path, even if it is more efficient in propellant. The fastest trajectories often involve the most demanding sequences. Gravity assists can also lengthen the path, even as they shorten the time to the final boundary. A spacecraft might take a detour inward toward the Sun or outward toward a distant planet to set up an assist. It might loop through the inner solar system to gain speed in stages. The distance travelled along the path may be longer than a direct route, but the final outward speed may be higher, and that higher speed can dominate the long cruise. Because leaving the heliosphere is a decades-long cruise, even modest increases in residual speed can reduce total time more than a shorter early path would. This is why some missions appear to wander on a diagram yet still reach the outskirts sooner than a simpler-looking path might. The Sun can also play a role in energy gain through the Oberth effect. A spacecraft can use a gravity assist to drop inward toward the Sun, reaching very high speed at close approach, then perform a propulsion burn there to gain a large increase in heliocentric energy. This strategy can yield higher outbound speeds than a burn performed far from the Sun with the same propellant. In principle, it can shorten the time to the heliopause significantly. In practice, it demands a spacecraft that can survive extreme solar heating and intense radiation near perihelion. It also demands a high-thrust propulsion system capable of performing a strong burn in a short time at that point. The engineering difficulty is substantial, and the mission risk rises. This strategy shows that faster exits are possible within physics, but it also shows that the path to speed is not simple. It requires pushing vehicles into harsh environments and relying on complex sequences that must work precisely. Even with gravity assists, there is a ceiling on outbound speed for practical payloads. Planets move at speeds of tens of kilometers per second around the Sun. A gravity assist cannot add more than a fraction of that speed to the spacecraft's heliocentric velocity in a single encounter, and it cannot do so without controlling the direction. Multiple encounters can add speed in stages, but each encounter consumes time. The net result is that outbound speeds for current and near-future missions remain in the range that yields heliopause crossing. Times measured in decades, not years. Gravity assists can shave years, not compress decades into a short span. Gravity assists also do not help with every definition of leaving. They can accelerate a spacecraft out of the planetary region and out of the heliosphere, but they do not change the basic fact that the Oort Cloud scale is thousands to tens of thousands of astronomical units. At current speeds, even a gravity-assisted probe would require thousands of years to reach such distances. This again highlights that the meaning of leaving determines the timeline. Gravity assists are powerful within the scale of the outer planets and the heliosphere, but they do not bridge the gap to the farthest gravitational halo in human timescales. The use of gravity assists also affects spacecraft design choices that influence longevity. A spacecraft intended for a Jupiter assist must be built to survive Jupiter's environment and to operate reliably for years before reaching it. It must have a communication system strong enough to maintain tracking during cruise. It must have propellant reserves for corrections. It must have redundancy because a failure before the assist can end the mission. These requirements add mass. Added mass can reduce available launch energy and therefore reduce the baseline speed. Designers must balance these factors to find an optimal path, and the optimal path may not be the one with the maximum theoretical speed gain. It may be the one with the highest probability of still functioning at the heliopause decades later. Gravity assists therefore represent a trade between patience and momentum. They allow spacecraft to leave faster than engines alone would permit, but they demand waiting for alignments, enduring long cruises to encounter planets, and accepting operational complexity. They help explain why leaving the solar system is not just a matter of building a faster engine. It is a matter of fitting within a moving clockwork of planetary motions and building spacecraft that can survive long enough to benefit from that clockwork. With gravity assists clarified as a tool and a constraint, the next inward step is to remain in the cold outskirts beyond Neptune and consider the Kuiper Belt as a real region. This matters because many people treat passing Neptune as leaving, while others treat reaching beyond the Kuiper Belt as leaving. Understanding the belt's spread and sparsity makes it possible to describe how many years it truly takes to pass beyond the last major region of known solar system bodies before the heliosphere boundaries approached. Beyond Neptune, the solar system continues in a form that is quieter and more spread out. The Kuiper Belt is often described as a belt, yet it is better understood as a broad region of space populated by icy bodies on a range of orbits. These objects include dwarf planets and many smaller remnants from the solar system's formation. The region does not begin at a single boundary, and it does not end at a single boundary. Its density decreases gradually, and its members are separated by vast emptiness. For the question of how long it takes to leave the solar system, the Kuiper Belt matters because it is the last major population of known stable sun-orbiting bodies outside the planetary region. If leaving means going beyond the Kuiper Belt, then leaving is a journey measured in years to decades depending on speed. It is still far shorter than leaving any distant comet reservoir, yet it is longer than many assume when they picture Neptune as the edge. The Kuiper Belt occupies distances beyond Neptune's orbit, extending outward for many tens of astronomical units. Some objects have relatively circular orbits, while others have elongated paths that take them closer in or farther out. Some are in resonances with Neptune, meaning their orbital periods are locked in simple ratios that keep them stable over long times. This resonance structure shows that Neptune's gravity still shapes the region dynamically, even though Neptune itself is far away. The belt is therefore part of the solar system's gravitational architecture, not an isolated ring. When an outward-bound spacecraft passes Neptune's orbit, it does not necessarily pass through the densest part of the Kuiper Belt. The belt's members are not distributed evenly, and the spacecraft's trajectory is a narrow line through a huge volume. The probability of a close approach to a Kuiper Belt object is small, unless the spacecraft is deliberately targeted. Most outward probes will pass through the belt without coming near any large body. From the spacecraft's perspective, the belt is not a scenery of nearby objects. It is a statistical region, in which the chance of encountering an object is higher than it would be elsewhere, yet still very low. This is why the belt can feel invisible even as it is crossed. The time required to reach Kuiper Belt distances depends on the spacecraft's outbound speed after its last major propulsion event. A probe that has used a Jupiter gravity assist and then continues outward at a steady pace will cover several astronomical units per year. At that pace, reaching the inner Kuiper Belt region beyond Neptune may take a decade or more after launch, while reaching the outer portions of the belt may take additional years. The precise numbers vary by mission, but the broad truth remains. The belt is not reached in a few months. It is reached on multi-year timescales. Passing beyond it, depending on the chosen outer threshold, can take 1 or more decades. The Kuiper Belt also overlaps with a more scattered population known as the scattered disk, where objects have more eccentric and inclined orbits, often shaped by past interactions with Neptune. Some of these objects travel far beyond the main belt region. This complicates the idea of leaving based on solid body populations, because there is no sharp end. Even beyond the main Kuiper Belt, there can be scattered objects on long orbits. a spacecraft might pass beyond a conventional belt boundary and still remain within the realm of occasional sun-bound bodies. This again shows that object-based definitions create fuzzy edges. To leave the belt in any strict sense would mean going so far that the probability of encountering such objects becomes extremely low, which pushes the boundary outward and lengthens travel time. In the Kuiper Belt region, sunlight is weak. This affects the practical operation of spacecraft. Solar panels must be much larger to produce the same power as they would near Earth. Many deep space missions at these distances rely on radioisotope power systems. The limited power output shapes communication and science operations. Transmissions to Earth require high-gain antennas and long periods of sending data at low rates. The increasing distance also increases signal travel time, though the communication delay remains measured in hours rather than days at Kuiper Belt distances. This delay reinforces the need for spacecraft autonomy, but does not yet remove the possibility of human supervision. It is an intermediate region where the craft is still connected to Earth through a steady but thin thread of radio signals. The temperature environment also shifts. With weak sunlight, spacecraft rely on insulation and internal heat sources to keep electronics within operating limits. Radioisotope power sources provide both electricity and heat, which can be beneficial. Thermal control becomes a matter of retaining heat rather than shedding excess heat. This is a different engineering regime than the inner solar system where sunlight can overheat surfaces. For a mission intended to last decades, the ability to manage internal temperature without active failure-prone systems becomes part of survival. If leaving the solar system is defined as leaving the region dominated by the sun's small body populations, the Kuiper Belt represents a meaningful threshold, but it is still not the outermost. Even if the belt thins beyond a few tens of astronomical units beyond Neptune, the solar system's gravitational domain continues, and the sun's plasma bubble extends farther. A spacecraft that passes beyond the belt is still inside the heliosphere for many more years. It is still immersed in the solar wind, though. That wind becomes weaker and more structured. It still experiences the sun's magnetic field carried outward. In this sense, leaving the belt is not leaving the sun. It is leaving a region of relatively more common solid bodies, while still travelling through a solar-controlled plasma environment. The belt also provides a hint about why leaving is not a single number. If leaving means going beyond Neptune, a decade-scale mission can do it. If leaving means going beyond the Kuiper Belt, a multi-decade mission may be required depending on speed. If leaving means crossing the heliopause, then the belt is only part of the journey, and the total time becomes several decades for the fastest probes. If leaving means going beyond the comet reservoir, then the belt is not even close to the boundary, and the time extends beyond any human planning horizon for a single mission. These layered definitions are not merely semantic, they reflect real changes in environment. Beyond the belt, the density of solar system objects drops, the sunlight weakens further, and the interstellar environment begins to press more strongly against the solar wind. Yet the most decisive physical transition, the change from solar-dominated plasma to interstellar plasma, lies farther out at the heliosphere boundary. That boundary is not marked by a visible feature, but by a change in particles and magnetic fields measured by instruments. The Kuiper Belt, by contrast, is a region defined by orbiting bodies that can be catalogued and mapped over time. Both matter, but they answer different meanings of leaving. In many public descriptions, leaving the solar system is equated with leaving the heliosphere because it defines a measurable transition into interstellar space. To understand the timeline for that transition, the next inward step is to focus on the heliosphere itself, beginning with the solar wind as the expanding medium that fills the space beyond the planets. This shift moves from object populations to plasma physics, from the quiet distribution of icy bodies to the flowing changing bubble that the sun creates around itself. The heliosphere is the sun's extended presence in space formed by the solar wind and carried magnetic field. The solar wind is a continuous outflow of charged particles that expands outward through the solar system. It shapes the space environment around planets, interacts with their magnetospheres, and fills the region beyond them with a thin moving plasma. This outflow does not end at Neptune or at the Kuiper Belt. It continues outward until it meets the surrounding interstellar medium, the local mixture of gas dust and magnetic fields between stars. Where these two environments press against each other, the Sun's wind bubble forms a boundary. If leaving the solar system is defined in a physical, measurable way, it is often defined as leaving this bubble because beyond it the local plasma conditions are no longer dominated by the Sun. The solar wind begins near the Sun's corona and expands outward at hundreds of kilometers per second. Close to the Sun, it is dense by space standards and it carries embedded magnetic field lines that spiral due to the Sun's rotation. As it flows outward, it spreads and becomes less dense. Its dynamic pressure decreases with distance, meaning its ability to push back against the interstellar medium weakens. Yet it persists over an enormous span. Even far beyond the planets, it remains present though thin. The heliosphere is not perfectly steady because the solar wind is not perfectly steady. The Sun's activity changes over an approximately 11-year solar cycle, with varying levels of sunspots, flares, and coronal mass ejections. During active periods, the solar wind can become stronger and more structured. During quieter periods, it can weaken. Over time, these changes propagate outward. A change in solar wind conditions near the Sun takes months to years to reach the outer heliosphere, because the wind must travel the distance. This means the outer boundary responds to the Sun with a delay. The heliosphere's size and shape can therefore expand and contract over time. It breathes on a multi-year rhythm driven by solar activity and by the ongoing pressure from interstellar space. The interstellar medium is not uniform either. The Sun moves through the local interstellar environment as it orbits the Milky Way. The density, temperature, and magnetic field of the surrounding medium vary on large scales. The heliosphere is therefore shaped by a moving interaction like a bubble carried through a flowing structured medium. In the direction of the Sun's motion, the heliosphere can be compressed. In the opposite direction, it can extend farther, forming a long tail-like region. This directional dependence matters for leaving because a spacecraft traveling outward in one direction may reach the boundary sooner than a spacecraft traveling in another direction, even if their speeds are similar. The heliosphere is also layered. Near the Sun, the solar wind is supersonic in the plasma sense. As it expands outward and encounters the interstellar pressure, it eventually slows. The location where it slows abruptly is called the termination shock. This is not a shock in air, but a discontinuity in a plasma flow where conditions change, speed drops, temperature rises, and the plasma becomes more turbulent. Beyond the termination shock lies the heliosheath, a region of slowed, heated solar wind that continues outward toward the boundary with interstellar space. At the edge lies the heliopause, where the outward solar wind pressure balances the inward pressure of the interstellar medium. These boundaries are not visible walls. They are identified by instruments that measure particle densities, flow directions, temperatures, and magnetic fields. A spacecraft approaching the termination shock may detect changes in energetic particles and in the structure of the magnetic field. It may detect a change in the flow of plasma. Approaching the heliopause, it may detect a drop in solar wind particles and a rise in particles of interstellar origin. It may detect a shift in magnetic field characteristics. The exact signatures depend on local conditions, and the boundary may be complex with mixing and irregular structures. The heliopause is therefore not a perfectly sharp transition in every measurement, but it represents a meaningful change in the dominant plasma population. For the question of how long leaving truly takes the heliosphere matters, because its boundary lies at distances on the order of 100 or more astronomical units in many directions. This distance is far beyond the planets, yet still small, compared with the distance to the nearest stars. It is a boundary that current spacecraft can reach in decades, which is why it has become a practical marker of leaving. It is also a boundary whose distance can be discussed with real data, because spacecraft have measured it directly. This gives the question an anchor in observation rather than in inference. The size of the heliosphere is often described in terms of where the heliopause is encountered along a particular trajectory. Because it varies with direction and time, it is better understood as a range. A spacecraft travelling outward may encounter the termination shock first, then traverse the heliosheath for years, and then cross the heliopause. The time spent in each layer depends on speed and on the thickness of the heliosheath along that path. For a fast probe, the heliosheath crossing can still take years. This illustrates again that leaving is not an instant. Even after a spacecraft reaches the outer heliosphere, it must still travel through an extended transitional region before it fully enters interstellar plasma conditions. The heliosphere also influences the radiation environment. The solar wind and magnetic field modulate the intensity of galactic cosmic rays entering the inner solar system. Inside the heliosphere, cosmic ray intensity is reduced compared with the interstellar environment, though not eliminated. As a spacecraft moves outward and approaches the heliopause, it gradually enters a region where the shielding effect of the heliosphere weakens. Beyond the heliopause, the spacecraft is more directly exposed to the local interstellar cosmic ray environment. This is another reason the heliopause is treated as a meaningful boundary. It corresponds to a change in the protective influence of the Sun's extended magnetic field. For human missions, leaving the heliosphere would likely not be an immediate goal, because the heliosphere provides some reduction in cosmic ray intensity, and because the distances are so large that travel would take decades with current technology. Yet for the question of leaving the solar system as a concept, the heliosphere provides the most physically grounded definition that can be measured on mission timescales that have already been achieved. It is the boundary that turns the phrase leave into a measurable event rather than a poetic idea. The heliosphere's complexity also means that the exact moment of leaving can be uncertain without careful measurement. A spacecraft might pass through regions of mixed particles or fluctuating fields. The boundary might ripple with solar activity. Instruments might fail or have limited sensitivity late in the mission. Thus, even when a spacecraft physically leaves, confirming the crossing requires functioning sensors and careful interpretation. The timeline to leave in a human sense includes not only the travel time, but the time required to gather and interpret data that shows the boundary has been crossed. With the heliosphere established as a measurable domain, and its boundary framed as a key marker, the next inward step is to focus on the termination shock region more directly. This is the first major transition in the outer heliosphere. It marks where the solar wind changes from a fast outward stream to a slowed heated flow. Understanding where this occurs and what it implies for travel time helps keep the path to leaving clear and layered, moving steadily outward through the Sun's fading reach before reaching the final heliopause crossing. The termination shock is the first major physical transition encountered on the way to the heliosphere's edge. It is the point where the solar wind, which begins as a fast outflow from the Sun, slows abruptly as it begins to feel the counterpressure of the surrounding interstellar medium. This transition does not mark the end of the Sun's influence, but it marks a change in the character of that influence. Inside the termination shock, the solar wind streams outward in a relatively coherent flow. Beyond it, the solar wind becomes slower, hotter, and more turbulent, forming the heliosheath. For the timeline of leaving the solar system, the termination shock matters, because it is a waypoint that some spacecraft can reach within a few decades, and because it begins the long final approach to the heliopause. The solar wind expands outward and thins as it travels. If it expanded forever into a vacuum, it would remain supersonic in the plasma sense. But interstellar space is not a vacuum. The Sun moves through a local interstellar cloud containing gas and a magnetic field. This surrounding medium presses inward. At some distance, the outward solar wind pressure becomes comparable to the inward pressure. Because the solar wind is a flowing plasma, it responds by forming a shock where the flow transitions to a slower regime. The shock is not a rigid surface. It can move inward or outward over time depending on solar wind conditions and interstellar pressure. It may also be irregular with structure on different scales. Yet it remains a definable transition that can be detected by instruments. A spacecraft approaching the termination shock may observe changes in the population of energetic particles. In the outer heliosphere, there are particles that are accelerated by the shock and by related processes. These particles can increase in intensity as the shock is approached. A spacecraft can also observe changes in the solar wind itself, including its speed and temperature. Though measuring the solar wind directly at great distances can be challenging if the relevant instruments are limited, or if the solar wind becomes too tenuous for some sensors. Magnetic field measurements can also show changes in turbulence and in the character of fluctuations. These observations help identify the transition. The termination shock does not have a single fixed distance from the Sun. It is better described as a range that depends on time and direction. The heliosphere is shaped by the Sun's motion through the interstellar medium and by variations in solar wind pressure. A stronger solar wind can push the termination shock outward. A weaker solar wind can allow it to move inward. These shifts occur over years because changes must propagate outward at the solar wind speed. Thus, a spacecraft's crossing time depends not only on its own speed, but on the evolving position of the shock during the years of its approach. Two spacecraft traveling in different directions can cross at different distances. The same spacecraft might approach during one phase of the solar cycle and cross during another. The shock's motion adds a gentle uncertainty to the timeline, for the purpose of understanding how long leaving truly takes. The termination shock is useful because it marks the transition from the outer solar system to the outer heliosphere. Before reaching it, a spacecraft travels through regions where the solar wind is still relatively steady and where the general environment is an extension of the planetary space environment, though thinner and colder. After crossing it, the spacecraft enters the heliosheath, where conditions become more complex. The heliosheath is not a thin layer. It can be tens of astronomical units thick. Crossing it can take many years. This means that reaching the termination shock is not close to leaving. It is closer to beginning the final long segment. The heliosheath is a region where the solar wind has slowed and heated, and where its flow may be diverted. It can become turbulent and irregular. The slowed plasma piles up and interacts with interstellar particles. Some neutral atoms from interstellar space can enter the heliosphere because they are not deflected by magnetic fields. When they interact with the solar wind, they can exchange charge with ions, creating energetic neutral atoms that travel in straight lines and can be detected by dedicated instruments. These processes contribute to the complex structure of the heliosheath. While these details are scientific in nature, their practical implication for leaving is that the boundary region is extended and dynamic. A spacecraft does not approach a neat surface. It passes through a broad zone of changing particle populations and fields. The time it takes to reach the termination shock depends on spacecraft speed, but it also depends on mission path and on whether gravity assists have been used to increase outbound velocity. A faster spacecraft reaches it sooner. Yet even for a fast outbound probe, the timeline is measured in decades because the distance is so large compared with typical spacecraft speeds. This is a key moment where intuition often fails. A spacecraft can pass Neptune in about a decade on some trajectories, yet it can take another decade or more to reach the termination shock. The reason is distance. The termination shock lies much farther out than Neptune's orbit, and the spacecraft's outward speed far from the Sun is not dramatically higher than it was near Neptune. It is a long coast. The termination shock also illustrates how leaving is entwined with the longevity of spacecraft systems. A probe must remain operational for many years to measure the crossing. Power must remain sufficient. Communications must remain possible. Attitude control must remain stable. Instruments must remain calibrated. The crossing itself is not a dramatic impact. It is a change in measured conditions. If instruments are off or degraded, the change might be missed or hard to interpret. Thus, the true time to leave includes not only travel time, but the endurance of the measuring capability. A spacecraft that survives to the termination shock has already demonstrated decades of reliability. A spacecraft that survives beyond it must continue to do so for additional years to reach the heliopause. In the broader structure of defining leaving, the termination shock is still inside the Sun's plasma domain. It is a change in the solar wind's state, not the end of the solar wind's dominance. Beyond it, the solar wind continues outward, though slowed and shaped by interactions. The heliopause remains ahead. For a traveller, the termination shock can be thought of as entering the outer surf zone before reaching the shoreline where the solar wind meets interstellar space. The analogy remains quiet and practical. A region of changing conditions precedes the boundary itself. The termination shock's existence also helps explain why leaving is not simply a matter of reaching a distance. The boundary structure is physical and dynamic. It is formed by pressure balance and flow transitions. If the interstellar medium's pressure were different, the termination shock and heliopause would be at different distances. If the Sun's wind were stronger or weaker over long times, the structure would shift. The solar system's plasma boundary is therefore a living structure shaped by a long interaction between the Sun and its galactic environment. A spacecraft leaving the solar system in plasma terms must traverse this living structure, and its timeline is therefore tied to conditions that are not under the spacecraft's control. After the termination shock comes the heliosheath, and then the heliopause. The heliopause is often treated as the moment of leaving because it marks entry into interstellar plasma. To understand the true duration, the next inward step is to focus on the heliopause boundary itself, what it is, how it is detected, and why crossing it can occur many years after the termination shock, even for spacecraft that are already far beyond the planets. The heliopause is the boundary where the Sun's outward-flowing plasma environment yields to the surrounding interstellar plasma. It is often described as the edge of the solar system because it is a physical transition that can be measured directly, unlike the inferred outer comet reservoir or the diffuse region where the Sun's gravity slowly gives way to the galaxy's tides. Yet the heliopause is not a solid shell. It is a surface of balance and mixing shaped by pressure magnetic fields and the Sun's motion through the local interstellar medium. For a spacecraft, reaching it takes decades with current speeds, and crossing it is not felt as a jolt. It is recognized through instruments that register a shift in particles and fields. This makes the heliopause a quiet but definitive marker of leaving in the most operational sense. The heliopause forms because the solar wind expands outward and pushes against the interstellar medium. The solar wind carries the Sun's magnetic field outward, creating a region where solar magnetic structure dominates the plasma. The interstellar medium has its own magnetic field and its own plasma pressure. Where these pressures balance, the boundary forms. Inside, solar wind particles are more abundant. Outside, interstellar particles are more abundant. The transition is not necessarily sharp in every property, because turbulence and instabilities can create regions of mixing. Still, the heliopause represents a change in which environment sets the baseline conditions. A spacecraft approaching the heliopause from inside has already crossed the termination shock and travelled through the heliosheath. In the heliosheath, the solar wind is slowed, heated and deflected. The flow becomes more chaotic. The density and energy of particles can fluctuate. The magnetic field can show complex variations. This region can be tens of astronomical units thick, so a spacecraft may spend many years in it. The time to cross the heliosheath is a major part of the time to leave, and it varies with direction and with solar conditions. A spacecraft cannot take a shortcut through it unless its speed is higher, and higher speed is limited by what the mission can achieve at launch and through gravity assists. Identifying the heliopause relies on multiple measurements. One of the clearest indicators is a drop in the density of solar wind particles, because beyond the heliopause the solar wind is no longer the dominant plasma. Another indicator is an increase in the intensity of galactic cosmic rays, because the heliosphere partially modulates cosmic rays. As a spacecraft moves outward, it can observe a gradual change, but at the boundary there can be a more noticeable step, where cosmic ray intensity increases and stabilizes at a higher level consistent with interstellar conditions. Magnetic field measurements also matter. The direction and behavior of the magnetic field can change across the boundary, though the details can be complex because solar and interstellar magnetic fields can drape and interact in ways that create layered structures. No single measurement alone defines the crossing perfectly. A robust identification uses a combination of particle data, cosmic ray behavior, and magnetic field characteristics over time. The heliopause is not fixed in distance. It responds to solar wind pressure, which changes with solar activity, and to the surrounding interstellar pressure. This means the heliopause can move inward or outward over years. Its shape can also be asymmetric because the Sun moves through the interstellar medium, compressing the front side and extending the downwind side. For an outbound spacecraft, the direction of travel matters. A craft heading in one direction might reach the heliopause at a smaller distance than another craft heading elsewhere. The heliopause might also shift outward just as a craft approaches adding time, or it might shift inward and be crossed sooner. These variations are not huge compared with the overall distance, but over a mission lasting decades they can add or subtract years. This is part of why the question of how long it truly takes is best answered as a range rather than a single number. The crossing itself is quiet because the densities are extremely low. There is no atmosphere to push against. There is no shock wave experienced by the vehicle. What changes is the statistical behavior of particles. Instruments detect that fewer particles have the energy distribution typical of the solar wind, and that more particles show characteristics of the interstellar medium. Cosmic ray detectors show that the modulation by the heliosphere has diminished. Over weeks to months, the data indicate that the spacecraft is no longer inside the Sun's plasma bubble. From an engineering standpoint, the spacecraft continues to cruise its motion, unchanged by the boundary in any noticeable way. The meaning of the crossing is scientific and definitional, not mechanical. The heliopause is also a boundary and shielding context. Inside the heliosphere, the solar wind and its magnetic field reduce the intensity of some cosmic rays compared with the interstellar environment. This reduction is not complete, but it is meaningful. Beyond the heliopause, the spacecraft is exposed to the local interstellar cosmic ray environment more directly. For a probe, this may be manageable with radiation-hardened electronics and error-correcting software. For human travel, it would raise long-term exposure concerns. Yet human missions that would reach the heliopause would already be on multi-decade timescales, making biology and life support the dominant constraints. The heliopause crossing would thus be a late-stage transition layered on top of many earlier limits. In practical terms, the heliopause is the boundary that can be measured with existing technology and within mission durations that have already been achieved by robotic probes. This makes it the most relevant definition of leaving for a question that asks how long it would truly take. If the boundary is defined as the heliopause, then the answer is decades for current probe speeds. If the boundary is defined as beyond the Kuiper Belt, the answer can be shorter. If the boundary is defined as beyond the Oort Cloud, the answer becomes many thousands of years. The heliopause sits in the middle, far beyond the planets, but not beyond all solar gravitational influence. It is therefore a practical compromise between an easy definition and an unreachable one. The time from Earth to the heliopause can be thought of in phases a few years to reach Jupiter. If an assist is used, a decade-scale span to reach Neptune's orbit, another decade or more to reach the termination shock, and then many additional years to cross the Helios heath and reach the heliopause. The exact division varies by mission. A probe might reach the outer planets on a different schedule. It might cross the termination shock earlier or later, depending on the solar cycle and the direction of travel. Yet the broad pattern remains. The early solar system is crossed in a smaller fraction of the total time. The final boundary is reached after long coasting through the outer heliosphere. The heliopause also forces attention to what it means to confirm leaving. A spacecraft that crosses the heliopause after decades must still be alive in a practical sense. It must have power. It must be able to point its antenna. It must have functioning instruments. If it cannot transmit data, the crossing might remain unknown. Thus, the true time to leave in a human-recognized way includes the endurance of systems and the ability to interpret measurements. The ship might physically leave before the data are fully analyzed because data return and scientific confirmation can take additional time. The crossing is a process of evidence rather than a single announcement. With the heliopause described as the key boundary for a measurable definition of leaving, the next inward step is to anchor these ideas in the record of real spacecraft. Actual outbound probes provide observed timelines how long it took them to reach the outer planets, the termination shock and the heliopause. Using these examples grounds the answer in achieved speeds and achieved endurance, showing what truly take means when the only available travelers are machines that have already been in flight for decades. The most grounded way to understand how long it truly takes to leave the solar system is to look at spacecraft that have already done it, or that are steadily on their way. These missions provide real outbound speeds, real power limitations, and real multi-decade endurance. They also show how the definition of leaving matters. A probe can pass the orbit of Neptune and still be deep inside the heliosphere. It can travel for years through the Helios sheath after crossing the termination shock. It can physically cross the heliopause in a moment, yet the confirmation of that crossing can take time because the evidence is built from measurements rather than from a visible marker. The Voyager missions are the clearest anchors because they travel far enough and long enough to sample the outer heliosphere directly. Voyager 1 and Voyager 2 launch in the late 1970s when deep space electronics, onboard computing and power systems are far less capable than those used in later decades. Their outward motion depends mainly on their initial launch energy and on gravity assists during encounters with the giant planets. After their last major planetary encounters, they become coasting travelers. Their outward speeds remain high by historical standards, yet they are still only tens of kilometers per second. Over decades, that steady speed becomes distance, and distance becomes boundary crossings. The first major reality these spacecraft show is that the outer planets are reachable within a human career span, but the heliosphere boundary is farther still. Voyager missions reach Jupiter in roughly 2 years after launch, then continue to Saturn. Voyager 2 continues onward to Uranus and Neptune, building a longer planetary tour. These planetary milestones occur within the first dozen years. They are dramatic moments in the story of exploration, yet they represent only the beginning of the long outward cruise. After the planetary flybys, the spacecraft continue to travel outward through a region where there are no more planned gravitational boosts. From that point onward, leaving becomes a test of endurance and steady motion, not a series of close encounters. The next anchor is the termination shock. Voyager 1 detects the crossing of the termination shock in the mid-2000s at a distance from the Sun that is far beyond the orbit of Neptune, yet still well inside the heliosphere. Voyager 2 crosses later, also in the 2000s. The two crossings occur at different distances, showing that the termination shock is not a perfect sphere, and that its position can vary with direction and with solar conditions. This is important because it demonstrates a subtle point about timelines A mission can have the same approximate speed as another and still reach a boundary at a different time because the boundary itself is not fixed in one place. The termination shock also marks the beginning of a long segment. After crossing it, both spacecraft spend years travelling through the Heliosheath, a region that is thick enough that it cannot be treated as a thin shell on the way out. The heliopause crossing provides the key time anchor for leaving under the plasma definition. Voyager 1 crosses the heliopause in the early 2010s. The crossing is later confirmed through the behaviour of particle populations and cosmic ray intensity, and the public confirmation follows after careful analysis. Voyager 2 crosses the heliopause later in the late 2010s, and its instruments provide additional confirmation that the boundary is real and measurable. The two crossings occur at distances that are broadly similar but not identical, again reflecting that the heliopause is shaped by direction and by time-varying solar wind pressure. These crossings make the timeline concrete. From launch to heliopause is measured in multiple decades, not because the spacecraft is weak or slow by everyday standards, but because the distance is immense relative to achievable cruise speed. The data also show that the last segment is not a short final approach. Years pass between the termination shock and the heliopause. This is the Heliosheath traversal, a long outward walk through a changing plasma environment, where the solar wind is slowed and turbulent. For the question of leaving this means that even after a spacecraft reaches the first clear outer transition, it still has many years to go before it can be said to be in interstellar space by the heliopause definition. The Voyager record also clarifies the difference between physical leaving and known leaving. A spacecraft crosses the heliopause at a moment in time and continues onward. Yet mission teams and the scientific community establish the crossing through patterns in data, sustained changes in cosmic ray intensity, sustained reductions in solar wind particle signatures, and magnetic field behavior consistent with the interstellar environment. These patterns must be observed over time to avoid mistaking temporary fluctuations for a boundary crossing. Then the data must be transmitted back to Earth, which can take hours of signal travel time and long periods of low data rate. Then the data must be analysed. The public moment of confirmation can therefore occur later than the physical crossing. This delay is part of what it truly takes to leave in a human sense, because leaving becomes a measured conclusion, not a dramatic instant. The probes also show how power and aging shape long timelines. Voyager spacecraft use radioisotope power sources that steadily decline in output over time. As decades pass, the available electrical power decreases, and the mission must turn off instruments and heaters to conserve what remains. This does not slow the spacecraft, but it can limit the ability to measure and transmit. In the context of leaving, this matters because a spacecraft can continue moving outward, regardless of whether it can report. A probe can be beyond the heliopause and still become silent, leaving its later progress unknown. The Voyager missions illustrate the practical edge of this, where instrument suites are gradually reduced to preserve essential functions. Their ability to confirm boundary crossings depends on having the right instrument still operating at the right time. Another spacecraft, New Horizons, provides a different kind of anchor. It is launched decades after Voyager with modern electronics and mission design, and it travels outward with a high initial speed, including a gravity assist at Jupiter. It reaches Pluto in less than a decade after launch, demonstrating how quickly a fast mission can reach the Kuiper Belt region compared with earlier missions. This creates a clear contrast between leaving the planets and leaving the heliosphere. A spacecraft can reach Pluto and even move beyond it, while still being far inside the heliosphere boundary. From the perspective of leaving, this shows that reaching the Kuiper Belt, while impressive, is not the same as entering interstellar space by the heliopause definition. It also shows that a fast start does not eliminate the long cruise to the heliopause. The boundary is still far beyond the Kuiper Belt, and the remaining travel time is still measured in many years. New Horizons also illustrates another practical detail: mission priorities and power use. Even with a radioisotope power source, power remains limited and instruments are used carefully. A mission can be designed primarily for a close flyby and then extended outward, but the ability to continue gathering data for decades depends on operational choices. In this sense, leaving is not only physics and distance, it is also the willingness to sustain a mission over long time spans, maintaining tracking, communications, and engineering support. A spacecraft can travel outward without attention, but confirming its environment and milestones requires continued engagement. The real record also clarifies what leaving does not require. It does not require continuous propulsion. The farthest proceeding probes do not thrust for decades, they coast. Their steady outbound motion comes from momentum gained early. This is why travel time depends so much on the initial energy and on gravity assists. It also means that once a spacecraft is on its long outbound cruise, the remaining time is largely set. Small trajectory corrections can refine pointing and path, but they do not radically change the time to reach a boundary. The clock is established early and the rest is endurance. The observed boundary distances are also useful for honesty about variation. Voyager 1 and Voyager 2 cross the termination shock and heliopause at different distances. This shows that asking how long it takes to leave should be answered with a range, because the boundary can be closer or farther along different directions and under different solar conditions. It also shows that there is not one solar system edge. The heliopause is a boundary of plasma dominance, not of gravity, and it is shaped like a bubble in motion with a front and a tail. A spacecraft heading into the compressed side may reach the heliopause sooner than one heading into a more extended region. The direction of travel chosen at launch can therefore change the leaving timeline even if cruise speed is similar. When these real missions are held together, a stable picture forms. Leaving the planetary region, meaning passing beyond Neptune's orbit, is achievable in about a decade for a fast mission, sometimes longer, depending on trajectory. Leaving the Kuiper Belt region, in the sense of moving beyond the main population of known icy bodies, can take additional years to decades, depending on how far outward the chosen threshold is and how fast the spacecraft is. Leaving the heliosphere, meaning crossing the heliopause into interstellar plasma, takes multiple decades at the outbound speeds that have actually been achieved by the fastest long-lived probes. Leaving the far comet reservoir, if it extends as inferred, would take thousands of years at those same speeds, making it a different kind of question entirely. These are not estimates drawn from optimism. They are anchored in the measured progress of spacecraft that have already been travelling since the late 20th century. They show that the phrase "truly take" is best answered by separating definitions and then matching them to real speeds. The next inward step is to consider what could plausibly make these timelines shorter without changing physics, higher departure energy, stronger gravity assist sequences and mission designs that prioritize outward speed while still preserving enough power and reliability to confirm the crossing. The record of existing probes sets a baseline decades to cross the heliopause with proven outbound speeds and proven spacecraft endurance. The question then becomes whether near-future designs could shorten that time in a way that remains within known physics and realistic engineering. Shortening the timeline means increasing the spacecraft's residual speed far from the Sun, because most of the time to reach the heliopause is spent coasting through the outer heliosphere. Faster early motion near Earth matters less than faster long-term cruise, unless that early motion translates into a higher escape energy that persists. Any strategy that meaningfully reduces travel time must therefore deliver a higher final outbound speed, and must do so without making the spacecraft too fragile to survive for the decades it will still require. One straightforward path is higher launch energy. If a launch vehicle can deliver a spacecraft onto a higher energy solar escape trajectory, the spacecraft begins its outward journey with a higher speed relative to the Sun. This reduces the time to reach every boundary outward. The limitation is the mass energy trade. Increasing departure energy reduces payload mass for a given launch system. If payload mass shrinks too much, the spacecraft may lack power communications capability and redundancy, reducing the chance of surviving to the heliopause and sending data. A near-future fast exit mission must therefore balance speed against endurance. For leaving in a measured sense, endurance is not optional. It is part of the definition. Another path is improved gravity assist design. A mission can use Jupiter more effectively by selecting a flyby geometry that maximizes outbound speed in the desired direction. It can also add additional assists such as Saturn to further reshape the trajectory. Yet each additional assist requires time to reach the planet and requires alignment. If the goal is to reach the heliopause sooner, the mission must consider whether the extra time spent reaching an additional assist is compensated by the higher final cruise speed. Often the answer depends on the boundary distance and on the expected gain. Because the heliopause is tens of astronomical units beyond Neptune, even a modest gain in cruise speed can pay back over decades. But mission complexity also increases with each assist, and complexity increases failure probability. The fastest theoretical sequence may not be the fastest practical sequence when reliability is included. A third path is the use of the Oberth effect near the Sun. By dropping inward toward the Sun and performing a burn at very high speed near perihelion, a spacecraft can gain a large increase in heliocentric energy. This could produce higher outbound speeds than a similar burn performed farther out. In principle, this can shorten the time to the heliopause significantly compared with purely gravity assist-driven speeds. The challenge is that the spacecraft must survive near Sun conditions. Temperatures on exposed surfaces can rise dramatically. The thermal protection system must withstand intense heating while keeping internal systems within limits. The spacecraft must also perform a precise burn at the critical moment, requiring an engine capable of high thrust and reliable ignition after years in space. The burn itself consumes propellant, adding mass that must be launched. For a probe, these are difficult but not impossible challenges. For a near-future mission, the main question is whether the increased speed justifies the added complexity and risk. Electric propulsion offers another route, but it is often limited by power. High-efficiency electric thrusters can provide a large cumulative change in velocity if they can run for long periods. For an outward mission, this could be used to steadily increase heliocentric energy beyond what a single chemical departure provides. The obstacle is power generation far from the Sun. Near Earth, solar power is abundant and electric propulsion can be effective. Farther out, sunlight weakens and panels must grow. A spacecraft could use electric propulsion primarily in the inner solar system, then coast outward. This could raise final cruise speed somewhat. Yet the additional propulsion, hardware power systems and propellant add mass. The net gain depends on detailed design. Electric propulsion is also low thrust, so it does not create dramatic speed jumps. It adds speed slowly. This can be compatible with an outbound mission, but the mission must still survive the long cruise that follows. Beamed propulsion, such as laser-driven sails, is a more radical but still physics-consistent concept. If a powerful laser array can push a reflective sail, a very small payload can be accelerated to very high speeds without carrying its own propellant. This could reduce the time to reach the heliopause from decades to years for tiny probes. The major limitation is payload size and infrastructure. Scaling the concept to a robust instrumented spacecraft with a radio transmitter and long-lived power source is difficult, and scaling it to any human-capable habitat is far beyond plausible near-term engineering. For the question of leaving the solar system with a probe-beamed sails might become a pathway for much faster exits. For the question as most people mean it involving meaningful instruments and sustained data return, the approach remains challenging. It also does not solve the problem of deceleration, though deceleration is not necessary for simply leaving. Another set of improvements lies in spacecraft longevity rather than speed. Even if speed increases only modestly, a mission can still reach the heliopause sooner in a human sense if it is designed to operate reliably and to measure boundaries clearly. Better radiation-hardened electronics, more efficient power conversion, improved antenna design, and more autonomous fault management can increase the chance that a spacecraft is still functioning decades later. This does not change the travel time, but it changes the probability that leaving is confirmed and scientifically useful. In practice, a slightly slower mission with high reliability can be more valuable than a faster mission that risks early failure. For a question about truly taking this matters, because time to leave is only meaningful if the mission survives to record the moment. There is also the possibility of building larger spacecraft with more power and stronger communications, enabling higher data rates at great distances and allowing clearer boundary detection. Yet larger mass often means lower departure energy for a given launcher, unless launch capability grows. The history of deep space exploration shows a pattern larger, more capable spacecraft tend to move more slowly, unless launch vehicles or mission architecture compensate. Thus, improvements in capability do not automatically mean improvements in time to leave. They can even extend the timeline if mass grows faster than launch energy. For the near future, the most plausible reductions in heliopause travel time likely come from missions that prioritize high outbound speed and accept modest payload mass while still carrying durable power and communications. Such a mission might use a strong Jupiter assist and, if feasible, a near-Sun Oberth maneuver. It might aim for a direction where the heliosphere is expected to be somewhat closer. If successful, it could reach the heliopause earlier than past probes, yet the crossing would still likely be measured in more than a decade, not in a few years, unless the mission sacrifices payload robustness and relies on very small fast concepts. Even then, confirming the crossing requires instruments and transmission capability. These considerations clarify that there is no single near-future leap that turns the heliopause into a short trip. The physics of achievable speeds with practical mass and power keeps the timeline long. What can change is the range. Decades can become shorter decades for robust probes, and decades can become years for tiny experimental sails. For human travel, the timeline remains far beyond what is reasonable with current propulsion and life support. With plausible speed-ups and their limits now established, the final inward step is to synthesize the definitions and the real speeds into an honest range of years. This synthesis keeps the boundaries distinct and places each on a timeline anchored in what spacecraft have actually achieved and what near-future designs might realistically improve, producing the calm answer to how long it would truly take to leave the solar system. How long it would truly take to leave the solar system depends on what leaving is taken to mean. Because the solar system has layered boundaries, the honest answer is a set of timelines rather than a single number. Some timelines fit within a decade or two, others extend across decades, others extend beyond any practical human project reaching into thousands of years. The distances do not change with opinion. What changes is which boundary is treated as meaningful and what speed a spacecraft can realistically sustain for the long outward cruise. When these choices are made explicit, the time becomes clear and calm. If leaving means leaving the region of the major planets, then the boundary is often taken to be beyond Neptune's orbit. Neptune lies about 30 astronomical units from the Sun. A fast robotic mission can reach Neptune-scale distances in roughly a decade, sometimes longer, depending on trajectory launch energy and whether planetary flybys are used. A slower mission designed for heavy payload might take longer. Under this definition, leaving is a long mission, but still within the span of a human career. It is a timeline measured in years to a couple of decades. Yet this definition does not represent a fundamental environmental change. It represents leaving the main planetary neighborhood, not leaving the Sun's broader domain. If leaving means leaving the Kuiper Belt region, then the answer spreads out. The Kuiper Belt is not a sharp ring, but a broad zone that extends beyond Neptune and thins gradually. To go beyond the main concentration of known Kuiper Belt objects may require reaching distances several tens of astronomical units beyond Neptune. At typical outward probe speeds after planetary assist, this can add years to decades beyond the time to reach Neptune. A fast mission that reaches the Kuiper Belt quickly can still require additional time to move beyond it, because the remaining distance is significant, and the spacecraft's cruise speed becomes the limiting factor. Under this definition, leaving can still occur within a few decades for a fast probe, but it is not a brief extension beyond the Neptune timeline. It is a further long cruise into the cold outskirts. If leaving means leaving the Sun's plasma bubble, meaning crossing the heliopause into interstellar plasma, then the timeline lengthens substantially. The heliopause lies far beyond the planets at distances on the order of 100 astronomical units, or more along many directions, and it shifts with solar activity and direction of travel. A spacecraft must first move beyond the outer planets, then travel through the outer heliosphere. It may cross the termination shock, and then spend years crossing the heliosheath before reaching the heliopause. With outbound speeds that have been achieved by long-lived probes, this journey from launch to heliopause takes multiple decades. The record of spacecraft that have crossed or approached this boundary shows that this is not an abstract estimate. It is a lived timescale of deep space travel. Under this definition, leaving is something that can happen within a human lifetime only in the sense that the spacecraft can do it, while humans on Earth observe it aging and receding. It is not a short mission. It is a generational mission for the engineers who begin it, and for the teams who sustain it. Even within the heliopause definition, there is a range. A spacecraft's outbound speed depends on launch energy and on gravity assists. Its direction of travel influences how far the heliopause is along its path. Solar conditions can shift the boundary inward or outward over the years of approach. For these reasons, the time to heliopause crossing is best understood as a band rather than a fixed point. A slower probe might require a longer span, perhaps several decades more than the fastest. A faster probe designed primarily for high outbound speed might shorten the span, but it is unlikely to compress it into only a few years, unless the payload is extremely small and the propulsion method is unusual, such as a beamed sail concept. For robust probes with meaningful instrument suites and limited power, the realistic horizon remains decades. If leaving means leaving the region where the Sun holds a vast reservoir of distant comets, often associated with the Oort Cloud, then the timeline changes scale entirely. The inferred inner part of that reservoir begins at thousands of astronomical units, and its outer extent, if it reaches as far as often suggested, can be tens of thousands of astronomical units. At the outward speeds achieved by current probes, reaching even the inner distances would require many thousands of years. This is not a matter of poor engineering, it is a matter of scale. The distance is so large that decades become negligible. Under this definition, leaving the solar system is not a mission in the modern sense. It is a project that would outlast civilizations unless a radically faster propulsion capability exists. There is also a gravitational definition in which leaving means reaching a region where the Sun is no longer the primary gravitational influence on an object's long-term motion, compared with passing stars in the galaxy's tidal field. That transition is gradual and depends on time because stellar encounters and galactic tides act over long spans. This definition does not provide a crisp distance or a crisp time. It describes a regime rather than a border. For a spacecraft, the Sun's gravity remains significant for a very long time, and the Sun remains the nearest star by far. Under this definition, leaving is not a single event that can be marked. It is an ongoing fading of dominance that unfolds as distance grows, and as other gravitational influences become more comparable. For mission planning, this definition is usually less useful than the heliopause definition because it does not correspond to a detectable crossing. Putting these definitions together yields a calm set of answers. To pass beyond the major planets, expect roughly a decade or more for a fast probe. To go beyond the main Kuiper Belt region, expect additional years to decades depending on how the boundary is chosen. To cross the heliopause and enter interstellar plasma, expect multiple decades with proven technology and mission designs that have already succeeded. To travel beyond the inferred distant comet reservoir, expect thousands of years at current speeds. The phrase truly take includes another element confirmation. A spacecraft can pass a boundary physically, but the moment becomes meaningful only when it is measured and transmitted. Communications weaken with distance. Power declines over time for radioisotope systems. Instruments must still function. The mission must still be supported. Thus, the true timeline includes the probability of survival to the boundary and the ability to send evidence back. A fast mission that fails early has a short travel time in theory and no leaving in practice. A slower mission that survives can provide a real crossing date. In deep space, endurance is part of speed's meaning. With this in view, the simplest honest statement is that leaving the solar system can mean about a decade, if it means leaving the planetary neighborhood, and it more commonly means multiple decades, if it means leaving the sun's heliosphere and entering interstellar space. Anything beyond that, in the sense of leaving the sun's farthest gravitational halo, moves into thousand-year timescales with current propulsion. These are quiet answers shaped by distance speed and the layered nature of the solar system itself. After the timelines are laid out, the scale remains steady and the details settle into a single calm picture. A spacecraft that leaves the planetary region does not enter a new kind of space. It continues through the same quiet vacuum, still warmed faintly by sunlight, still guided by the sun's gravity. As years pass, the outward motion becomes a simple routine of coasting, tracking, and conserving power. The sun grows smaller in the sky, but it remains the brightest object for a long time. The radio signal to Earth takes longer to arrive, and the reply takes longer to return, and the exchange becomes a slow rhythm measured in hours. The craft's interior stays warm only because heat is managed carefully, and the electronics remain alive only because power is used sparingly. Beyond the Kuiper Belt, the space between objects becomes so wide that the idea of passing through a region is mostly an idea of distance on a chart. The spacecraft crosses it without noticing because it is not a wall. It is only a thinning population. Farther out, the solar wind changes from a steady stream into a slowed, heated flow, and the boundary layers of the heliosphere begin. The instrument's register shifts in particles and fields, not in view's outer window. The passage from the solar wind bubble into interstellar plasma arrives as a change in counts and patterns, and then it holds steady. The spacecraft does not feel the heliopause. It simply finds itself on the other side, still moving outward, still carrying the momentum it gained long ago, still inside the sun's gravitational reach, even as the sun's plasma influence fades. Beyond that, the distances become so large that years stop being a useful unit for some boundaries, and the idea of leaving becomes an idea of time that no single mission can comfortably hold. The outward journey remains possible for machines because they can endure long, quiet intervals. For human understanding, the honest comfort comes from keeping the definitions clear, letting each boundary have its own timescale, and letting the solar system remain what it is: layered, extended, and slow to cross.